So today we're going to do a little group theory proof. We're going to show that the kernel of a group homomorphism phi that maps from G to H is a normal subgroup of G, and we're going to assume that we already know that, the kernel is a subgroup of G. We're just showing that it's a normal subgroup, okay? And that's because I think showing that it's a subgroup is kind of boring, just, uninteresting. I think the cooler part is showing that it is a normal subgroup. So first let's review our definition of what a kernel is. So the kernel of a homomorphism phi is a set of all elements G in our set, in our domain big G, such that phi of G is the identity in the codomain of H in our case. So here I have our set G and our set H with the homomorphism phi mapping there, and the identity of H is going to be here, and I'm going to say that this box denotes the kernel of phi, okay, and so any element in here will be mapped to the identity, and so I can draw another as an example. So this guy will also be mapped there. And so all the elements in this box will be mapped to the identity in H, all right? So that's just a quick little visual for that. That's the whole point of the kernel. So now let's also review what a normal subgroup is, what it means for something to be a normal subgroup. So in this case, what we're trying to show is that the kernel of phi is a normal subgroup of G. And our symbol for a normal subgroup is like a little triangle pointing that way, basically, just like a less than sign, kind of like for the groups just closed off there. And this will, in other words, mean, so for something to be a normal subgroup of something else, we need that for all elements G in big G, and for all elements K in the kernel of phi. And so I'm saying that the K just is an element of the kernel. So every single element of G, of this guy, and every single element of the kernel, which, remember that the kernel, we already said it's a subgroup of G, meaning it's a subset of G. And so if the kernel is a subset of G, then this little element K is also going to be in G. But I'm just showing this for emphasis. So for all G in G and for all K in the kernel, we have that G inverse is inside of the kernel of phi. Okay, so that's basically what it means. This is the main part that we have to understand, the fact that it's G inverse. And so if we have that, if we show that, then we know that the kernel of phi is in G. Okay, so let's just begin. So basically, if we have GKG inverse, I mean, it only makes sense to start by taking phi of GKG inverse. So we can start doing that. So we have phi of GKG inverse. Okay, what's that going to be? Well, we can write that based on, because this is a homomorphism, we can write that as phi of G times phi of K times phi of G inverse, right? And remember that we're doing different operations here, so this group operation is the one from capital G, and this one is from the one in capital H, so just keep that in mind. This could be addition or something else, and this could be multiplication or something else. They could be the same, but let's just assume they're probably different. So, basically, okay, so GKG inverse maps to this, and phi of K, well, remember, K is in the kernel. So if K is in the kernel, that means that it's one of those elements in the big G, such that phi of G will map it to the identity of H. So phi of K is actually just the identity in H, right? So basically what that means is that we can rewrite this as phi of G times the identity in H times phi of G inverse. And let me actually write this like that. And that's because a homomorphism will map inverses to inverses. So it'll take G inverse, and it's going to map it to phi of G inverse through the homomorphism phi. Okay? So basically, we can kind of just ignore this identity now. Oops. We can say that this is phi of G times phi of G inverse, right? Because whenever you're multiplying by the identity, it doesn't do anything. It's like multiplying by 1 or adding 0, stuff like that, right? And when you have something like this, something times its identity, right? So this is like 5 times 1/5, or 3 minus 3. That is simply just the identity in H, right? Because remember, this is the stuff in H going on, so this will be the identity of H, okay? So let's see where we are. So we took this expression, and this expression is equal to the identity of H. And remember that the kernel of phi maps all of its elements to the identity in H. So that means what we have is that GKG inverse, when we take phi of that, it's the identity of H. So it's going to be true that the kernel of phi is a normal subgroup of G. So our statement is correct. So I'm going to put a little symbol here to show that we finished our proof. And yeah, so thank you guys so much for watching, and I will see you in the next video. Bye guys!